Alright, welcome back to the probability slides. Let's finish them up. Alright, so we were talking about conditional probability, and now we have a very major feature of conditional probability. It's called Bayes' theorem. It's a very exciting thing that everyone should know. So let's talk about it. So sometimes, like, we know the probability of B given that A occurred. Yeah? That's nice to know. We know also, usually it's easy to just get these normal ones. We know the probability of A and the probability of B. But what we really wanted this whole time was the probability of A given that B occurred. So the flip side of this one. You can get that. Here is the formula. Here is Bayes' theorem. The probability of A given B in terms of those other three things, in terms of the flip side, and just those individual probabilities of each, that's how you can access it. That's how you can flip it around, which is really cool. So let me prove that to you. This will go back to the definition of conditional probability. So the normal conditional probability, the way you would calculate it is E given F is the probability of their intersection over the probability of the second thing. So probability of F. Okay? So let's use that to our advantage. So let's start with what we have. Like, we have this one, so the probability of B given A, that's equal to the probability of A intersect B, I'll just put them in alphabetical order, over the second thing, probability of A, which we assume we know. Okay? We can use this to solve for probability of A intersect B, right? Just bring this to the other side by multiplication. So let's do that, because that's going to lead us closer to the answer. So the probability of A times the probability of B given A is equal to the probability of A intersect B, which is nice to have. That's another way to calculate it. Okay, so with that, we know what A intersect B is in terms of these things, and I think you know where I'm going with this. Now let's try and make this happen. But this is going to be the key. We can now plug that in for this one, because what is A given B normally, using this kind of notation? Well, the probability of A given B is the probability of their intersection, and set intersection is commutative, so probability of B intersect A is the probability of A intersect B. These orders don't matter. And then that's over the probability of B, which we also assume we have. And by that, I mean B. There we go. So what do you know? I need this. I have this. I assume that I have this. I have this. I have this. Let me just plug this right in here for that. And voila, we get that formula. Okay? So that's quite nice to have. And it's a way of flipping around what you're interested in. And that might give you some nice results sometimes. Finally, this is a fun thing to notice as well. If you don't know the probability of B, you're kind of forced to know the probability of A in order to make this whole thing work. But you technically don't need the probability of B if you also know the probability of B given that A did not occur, the probability of B given A complement. Okay? That is equal to this. The probability of B is equal to the probability of B given A times probability of A plus the probability of B given A bar, so A didn't happen, times the probability of A not happening. Okay? Let me prove that to you very quickly. That's another way to write this, is using these ideas, right? What is this but an intersection, right? This kind of multiplication, that's just an intersection. So this becomes the probability of A intersect B, adding that to the probability of, if you follow that theorem all over again, or this pattern all over again, this will give you the probability of A intersection, so the probability of A not happening, A bar, A complement, the probability of A not happening, and also B happening, intersected with B. And the reason that's equal to the probability of B, well, let me show this to you in a very tiny way. So here's A, here's B. The probability of just B is equal to, well, the probability of A intersect B, if there's anything there, so that's this bit. And now all we need is this bit right here, right? We need to get that 2, and that will give me all of B. So that's equal to, actually, that's equal to A complement intersected with B. Because what's A complement? It's everything in the universe that is not in A. So it's all this stuff, all of it. So that's everything. And then I just need to intersect that with B. You see that? That will give me this bit of everything that's in B but not in A. And together, those make all of B. Isn't that cute? So that is all I wanted to show you there. That's why that works. but Bayes' theorem, very, very useful. The classic example of Bayes' theorem is, you see this every time you learn it in every statistics textbook. It's like, how good is a test for a certain illness? And so this is very relevant nowadays, isn't it, for COVID and things like that. So here is my setup, and let me show you how nice Bayes' theorem is to us. Okay, so suppose that we have a test for an illness, like do you have COVID or something. The test is 90% accurate when someone has the illness. So that's saying this. The probability of you getting a positive result given that you had the illness, you see how conditional probabilities come into play here, that's equal to 0.9, 90%. And then let's pretend that the illness only happens in 5% of the population. So the probability just in general of you having the illness is 0.05. That means the probability of you not having the illness is the complement, right? So 1 minus that. It's a 95% chance that you just randomly pick a person and they don't have the illness. And now let's talk about accuracy when someone does not have the illness. Okay, so the probability that you get a negative result given that you were really not ill was 80%, 0.8. Okay, which means, on the flip side, the complement means the probability of you getting a positive result even though you did not have the illness is 20%. That's not 0. Okay, that might seem like a good test to us though. So our question now is, what is the probability that someone has the illness given that they got a positive result? Do you see how you'd want to know that? That's a very good statistic to want to find. It's the kind of the flip side of this one. This one's like 90%. It seems nice. What is this? Probability that you really do have the illness given that you got a positive result back. That's what we'd like to know. All right, so let's calculate this using Bayes' rule. What we need is probability of the opposite times probability of A over probability of B. Okay, so let's get started. We need to calculate, this is equal to, right? The question mark is equal to probability that you get positive given that you had the illness, I'll just say HI for that, times probability of A, which is the thing on the left, that's the probability of having the illness. Let me make sure that's correct. Probability of A, yeah, given B is the probability of the flip thing times the probability of the thing on the right for this. So yeah, it's the probability of having the illness over, we have, now we need the probability of this thing below. What's the probability of being positive? Okay, well, that's the probability of being positive, and I claim it's equal to this kind of idea here. These are things that we can calculate. Okay, so the probability of being positive, that is going to be the probability of the intersection, which is just this all over again, down here on the bottom now. P given has illness times probability of has illness plus the probability of that weird other intersection. B given A bar, which is just everything that we had before on the left, which is everything that we put here, but the opposite. So pattern finding, it's this probability given that you swapped this, so you don't have the illness. Probability that you're positive, but there is no illness. Let's say NI for no illness. And then we multiply that by, gosh, the probability of the second thing bar again, so the probability of not having the illness. I believe that is correct. Okay? So that should give us that probability that we were looking for, and we can fill these in. Probability of P given has illness, that's this, 0.9. Let me just fill them in now. 0.9 times 0.05 over, we have probability of, well, that's all the same over again. 0.9 times 0.05 plus, we have this as well. P given no illness, so that's 0.2 times probability of no illness, which is 0.95. And let's go off to Python to calculate this. I have something else that I'm going to show you later today, But let's take this here, and we have 0.9 times 0.05 over a big sum of 0.9 times 0.05 plus 0.2 times 0.95. And that looks to be about 19%. So 0.19, 19-ish%. So the probability that you have an illness, given that the test gave you a positive reading, is still very, very small. 19%, that's tiny. So was this really a good test? Maybe not. So that's a fun example. It's very counterintuitive. Like, all of these look like good numbers, but when they came together, it was not a good number in the end. What we really cared about was not right. Okay? So that's fun. That's a good example of Bayes. Let's keep on trucking. Let's talk about something called a random variable now. This is nice because it's kind of like computer science. So a random variable, usually with capital letters, that is a function, believe it or not. We define a random variable to be a function from the sample space, all the things that could happen in your experiment, to the real numbers. Okay? That's the idea. And because it's random, it's like every time you look at it, it changes. So think of it as a variable whose value could be anything, could always change. And here's just some notation. We give it a piece of the sample space. If you give it a subset, it gives you the range. Okay? So x of, give it the entire sample space, is the range of the function x, everything that it could hit. Okay? So here's a nice example from your book. Let's make a random variable, call it d, to represent the idea of rolling 2 dice. Okay? And our random variable d is going to keep track of the sum. Okay? It's going to keep track of the sum of all the numbers on the dice. Okay? So that means d could have been 5, right? Because we could have rolled a 3 and a 2 or a 2 and a 3. So d equals 5, our random variable being 5, is possible because of what it's supposed to represent. It's supposed to represent an outcome of rolling 2 dice and getting their sum. It's always a number for a random variable, though. So that means the range, okay, the range of our random variable d is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are all the numbers that you could get by rolling 2 dice and adding them together. Okay? That's the idea. And if this was like an outcome of our dice, let's call this, I don't know, this is event E happening. It's a function, right? So d of E is equal to 9. We're adding all of those numbers that we got by for those dice. Okay? That's essentially what's happening. It's taking an event, something happening, and giving back a number. Okay? And that's how you calculate the range. So it's a weird concept, but hopefully with more examples it'll make sense. Here's another example. Let's let another value, let's let m be the random variable that represents the sum of 2 spinners. So you have 2 spinners, that a red one and a blue one, that each hold 3 different options, 1, 2, or 3, and we can let m be the random variable that represents the sum of those 2 spinners. So say like we rolled these 2 in this way, we got this outcome. The blue one was pointing to 3, the red one was pointing to 2. Our random variable takes that outcome and just adds together those numbers. It gives back just a single number representing their sum. So that's what random variables do. They represent a numerical result to what happened in your outcome. So that's a random variable, and let's use that to do cool stuff. So first we need to talk about distributions of random variables. So the distribution of a random variable is how often each outcome, each value of that random variable occurs. Okay, so it's the set of pairs R, so that's an outcome, that's a number of that the random variable can generate, and then the probability that you ended up getting that outcome. Okay, the probability that your spinners added up to 5, for example. Okay, so for every thing in the range, every outcome in the range, it's just the probability of that each that random variable gave you that value. Okay, so for example, here are all the outcomes. Like here's all the ways to get 2 on your spinners. They both have to hit 1, right? They both got to be 1 and 1. So there's only one way to get there. You got this event. 1 on blue, 1 on red. There are 2 ways, though, to get 3 on your spinners. This one can be 1, this one can be 2, or this one can be 2, this one can be 1. 2 outcomes there. There's 3 ways to get 4 on your spinners. Here are all the possible outcomes. Does that make sense? 2 outcomes to get 5, 2 outcomes to get 6. And so now once you know all the possibilities, you can say, all right, there are 9 possible outcomes. And this event of it being 2, there's only one of those. So it's a 1/9 chance that you end up with your random variable being set to 2, for example. Okay? So this is your m. Our random variable is called m, and this is when m is equal to 2. This is all the ways. This is when m is equal to 3. There's 2 ways to make that happen. There's 3 ways to make m being set to 4. Okay? So that's the distribution of a random variable. So it looks like it's very likely to get a 4. That's what you can aim for, maybe, if you're making a bet. That's the most likely thing. And now let's talk about expectation. This is the whole reason we talk about random variables. The expectation of a random variable is a very important number to care about. Okay? It's called the expectation or the expected value. Okay? This is what it looks like. If our random variable is called x, we say e with brackets and then x in the middle of those brackets, kind of like an array lookup. We say e of x, this is like the expected value of the x random variable. And this is how you define it. It's a number again. It's for all the events, you take that number that the random variable gives you for that event, and you multiply it by the probability of that event occurring, and you add them all together. Okay? P of s is the probability of the outcome s. Sorry, that should be a lowercase s. Okay? So that's what you do. Alternatively, you can like simplify this because you know that these values, these outcomes might appear multiple times, and we've already gone and calculated the probability of all of them occurring at once. So you can do it like this as well. The expected value of the random variable x is all the outcomes, all the numbers that the random variable could take over, and then you take that outcome and you multiply by the probability of it occurring. Okay, so this will make sense for this example. I just wanted to say this in words, and x of s here is the range of that random variable, of the function x. Okay, so it's really just a weighted average. Sorry to use fancy terminology to get there, but it's really just a weighted average of what can you expect, like on average, what should the random variable give you back. Okay, so here's the expected value of our m random variable, and we're going to use this way to calculate it. It's like, okay, there is a 1/9 chance of you getting a 2 for your random variable, so we multiply 2 by 1/9. Okay, it's a weighted average of what number should we end up seeing really on average for our m random variable if we ever look at it, because it's a random number, right, throughout the range. There's a 2/9% chance that we end up with a 3, so we add that there. There's a 1/3 chance we end up with a 4, so we multiply those two and add them. 2/9 chance we end up with a 5, 1/9 chance we end up with a 6. And so if you do this calculation, you add them all together, the expected value of your m, if you look at it, and it's a random number, but we expect it to be 4 on average, which is kind of intuitive, like that's the most common thing. But it's like the 3s cancel out the 5s, and the 2s cancel out the 6s as well. Like if you expect a value, what you can expect to see from your random variable is essentially 4 on average. That's the idea. Okay? You can also do conditional expectations, like what is the expectation of our random variable m given that we saw a 1 on the blue spinner. So then we pick out all the ways that the blue spinner could have been 1, boop, boop. It looks like there's 3 ways, and then we build that weighted average. So it looks like it can only be 2, 3, or 4 if the blue spinner's 1. So this weighted average is, okay, it's 2 with a certain probability plus 3 with a certain probability plus 4 with a certain probability. And it's 2 1/3 of the time, right, when the spinner is blue, and it's 1. So 1/3 chance that it added up to 2. There's a 1/3 chance it added up to 3, and there's a 1/3 chance it added up to 4. And if you do this calculation, this ends up giving you back 3. So again, you can expect to see 3 from your random variable if you were to look at it. Like it's in a box. You open up the box. On average, you expect to see 3 over time. Okay? That's kind of what this means. So the expectation of a random variable, where a random variable is just a numerical result associated with your experiment. Okay? So with that, with a lot of explanations, let's talk about this. Let me give you a chance to try it. All right? So here's an experiment. We have a red die and a blue die, and we're throwing both of them. We're jumbling those numbers and getting back a reading. Okay? So let x be the random variable whose value is the product of the numbers on the red and blue dice. Okay? I think you can try all three of these, and then we'll do them all together. Okay, so what's the range of x? What are all the values that this random variable could take on, first of all? What's the distribution of the random variable x? Like, maybe you landed on a 2 and a 3, so one of the possibilities in the range is 6. What is the probability of you seeing a 6 for your random variable x, for that being the product? So give me that distribution, and then finally use that distribution to calculate the expected value. Okay? What is the expected value of your x random variable? Okay? So, first of all, remember all your options. So, like, let's say red die first, blue die second. So if the red die was 2 and the blue die was 3, then our random variable would give us back for this outcome the product. 2 times 3 is 6. Okay, so those are all the different possibilities. You could roll a 1 and a 1, so the outcome's 1. You could roll a 1 and a 2, so the outcome's 2. So you have all these different options, and here is a way to generate all of them. I've done it in Racket. So I'm counting the outcomes. This is how you make an empty hash table in Racket. And so I'm going through all the numbers. I is ranging from 1 to 6. J is ranging from 1 to 6. So those all the different ways that we could have rolled a pair of dice. And here is all the stuff. Here's the product of those two dice. And then we're going to keep track of how many times we saw a 1, a 2, a 3, and all that stuff. We're putting it into the hash table. Okay? And then I'm also calculating the expected value, but we'll talk about that later. So, Racket, scratch.racket. There it goes. So let's take this and bring it into our slides. So first of all, the distribution. What is the range of x? It's all these things before the colons. Here are all the numbers that you could get back from rolling 2 dice. I always get that wrong. So like 36 is the biggest option, right? Because they were both 6. But here are all the other numbers that you could get. 1, 2, 3, 4, 5, 6. Apparently you can't get 7, right? Because you have to multiply them. But there's 2 ways to get an 8, for example. You could roll a 4 and a 2 or a 2 and a 4. Does that make sense? There's only one way to get a 9. You have to roll, is it a 3 and a 3? Yeah, you're forced to roll a 3 and a 3. That's how that works. There's only one option. So, yeah, this is the counts. Okay, so for every time you see a 1, you count how many times you saw that 1. So there's only one way to get a 1 in the answer, because they were both 1. There's 2 ways to get a 2 ways to get a 3, 1 way to get a 36. And so we could add all these up. That's our total number, and print that, right? Like, I don't know what number that is, but it's something. And that will give us the distribution. Okay, so maybe we can print that, in fact. Dun, dun, dun. Print total outcomes. I think it's just, I'm keeping track in this variable called total outcomes. So let's print that here. There we go. So there's 36 possibilities. So let's replace our picture with this better one. There we go. So now we can just divide by 36. So the probability, the distribution would hold, like for 36, the idea of you getting a 36, there's only 1 out of 36 chance of you getting that. Okay? That's the idea. And that's how you build all this up. So this is the range is all these numbers on the left. And then you can calculate the distribution with these. Okay? So that's how we can calculate those. And then if you multiply them all together, you calculate the expected value. It's always, you add the probability of that outcome happening times that outcome occurring, right? The probability of it occurring times the number that your random variable sees. That's the product. And then you just keep on summing all of those into like some variable called expected value. And apparently the expected value is 12.25. So the probability, the number that you can expect to see over time on average from your random variable, which represents the product of the two numbers on the dice that you roll, is 12.25. So it's never a number that really exists, but essentially that's what you should see over time. That's what the random variable is trying to say. Okay? So that's quite helpful. So it looks like numbers around 11 and 12 and 13, those are what we can expect to see, which kind of makes sense. Like here's 12. It's very probable for you to roll 2 dice and see 12, for example. All right, so that's this. Hopefully we're getting some practice with that, and it's coming together in our brains. Let me tell you the last cool thing about expected values. Another reason why we use them, in addition to being just a nice number to tell us something cool about our experiment, we can also calculate new numbers, new random variables, essentially, with 2 existing random variables. That's really nice. And there's an easy way to calculate it using the idea of linearity of expectations. So if you have 2 random variables, like the sum of the dice and the product of the dice, for example, you can calculate the sum of them and make that a random variable. What is the sum of them? And actually, the calculation is super easy. It's just the sum of their individual expectations. This is called linearity. You can bring out the sum. You can just like distribute the expected value, essentially. And then also, if C is a real number, you can multiply any random variable by a real number, and you can just distribute that expectation to the random variable itself and just multiply whatever that expectation is by C. You don't have to do anything fancier, which is really cool. Okay? So it's the idea that you can push the expectation inwards. Push the expectation inwards. And that's very easy to calculate the new expectation based on you changing things around. Okay? This is called linearity of expectation. So let's talk about this. So we have this. Here's a nice proof. What is the expected value of E of this sum random variable? It's x plus y. So using the formula, go over all the outcomes. It's the probability of that outcome times whatever the expected value, whatever your random variables give back. And so we're adding those answers together, right? That's easy. And then, well, what is this but a bunch of numbers being multiplied together that you can distribute? And so you can make the equation look like this. And then you can just make 2 summations, like sum this part and this part. You can bring out the summation. That's not hard to do. That changes nothing, right? And then this form is just the expectation of x. And then that second form is just the expectation of y. It's super nice. Same for this one. If you want to calculate the expected value of c times a random variable x, well, the c is going to be in here now because that's the full value. But you can bring the c outwards, right? You can bring the c out behind this summation because it's not affecting anything. It's always going to be there. So you can just have it there once and for all after you've done the inner part, which is the expected value just times that c all over again. Okay? So it's very easy to make a new random variable based on existing ones, or and potentially also a constant that you want to multiply by. Okay? So let me show you an example of this and why it's useful. Linearity of expectations. So assume that the probability of a person born on a given day is 1 over 365. So really it's not that, right? So let's ignore leap years. In a group of 100 people, what is the expected number of pairs of people who have the same birthday? So this is finally coming full circle. Like, how would you use expected value in real life? Let's talk about this, okay? Let's talk about how we would calculate this. What is the expected number of pairs of people who have the same birthday? So first of all, how many different pairs of people are there? Because that's something we kind of have to usually divide by, yeah? So we have a group of 100. There are 100, choose 2, right? How are all the ways that we can take 2 people out of this group of 100? There are that many pairs of people, okay? So we can't forget about our combinatorics. And this is equal to 100 times 99 over 2, which is, let's figure it out. Let's figure out what that needs to be, because we want a number in the end. So that was 100 times 99, all that over 2, 4950. So that's the number of pairs of people possible. And here's the idea. We want to do this. Let's make a bunch of random variables. Let's make random variable P1, random variable p2, random variable p3, all the way to random variable p4950 for every possible pair of people. Let them be random variables. Let them be, we have to make a number for every random variable. They have to give back numbers, right? Let them be random variables that are 0 if the pair, that particular pair, does not share a birthday, share a b-day, and then 1 otherwise, and 1 if they do. So the random variable p1, like that particular pair of people, it's going to be set to 0 if they do share a birthday, or if they don't share a birthday, and 1 if they do share a birthday. Okay? And we need to calculate the expected value of the sum of all these random variables, p1 plus p2 plus ... all the way to p4950. Okay? That's equal to, using linearity of expectations, we can distribute that expectation. It's the expectation of p1 plus the expectation of p2 plus ... all the way to the expectation of that last random variable, p4950. Let me draw that better, even though it's small. We just need to figure out what each individual expectation is now. And here it is. The expected value, right, for a pair of people, that's equal to, well, what are the possible outcomes? What's the weighted average, right? Well, the random variable could have been 0 if they didn't share a birthday. What's the probability that those two people did not share a birthday? Well, it's a 364 out of 365 chance, right, that they had different birthdays. Does that make sense? That's essentially what's going on here. There's only a 1 in 365 chance that they both had the same birthday, because we're picking a random day, right? So the answer is 1 there times that. This is our weighted average. So it was 0 with this chance, and it was 1 with this chance. And what do you know? This expected value is 1 over 365. Because this goes away to 0. And this is our answer, 1 over 365. That's the expected value of this random variable, which tells us this answer, this expected number of pairs of people who share the same birthday. Well, now that I know all of these are equal, it's just, well, there's 4950 of them. It's 4950 times 1 over 365. Okay? Which is equal to, apparently, I did this before, but we can do it again. 4950 times 1 over 365, so just divided by 365, 13.6. So you can expect to see 13.6 pairs of people in a group of 100 who share the same birthday. And that's an interesting thing to notice, okay? And linearity of expectations gave us the answer quite easily. We just needed to notice that, oh, it's the same for everybody. This is the expected value of this random variable, set to 1 if they share a birthday and 0 if they do not. Okay? So that's a fun one. And I think I have, gosh, one last topic to tell you for these slides, and then we'll just practice them and look at cool stuff. Let's talk about what's called the binomial distribution. Okay? Here it is. The binomial distribution has to do with experiments that can have only 2 outcomes in the end, like flipping a coin. Success or failure, we say, is the outcome. Like heads is success, failure is tails, for example. And experiments with only 2 outcomes are also called Bernoulli trials. Okay? This is the dude who invented this binomial distribution. And so let's talk about it. The distribution over the random variable defined by the number of successes, okay? Number of successes of you doing a bunch of these Bernoulli trials, flipping a coin, for example, that's called a binomial distribution. So we're caring about how many times we can get a success, how many times we can get heads. Like if we flip a coin 10 times, for example. So think, because these are 2 outcomes, the easy thing to think about is coin flipping. Okay? And so here's what Mr. Bernoulli came up with. The probability of exactly k successes in a sequence of n independent Bernoulli trials, so they have to be independent in that, like, you flipping a coin on trial 1 does not influence the outcome of the coin on trial 2. I think that's normal to expect, right? And if the probability of success, getting heads, for example, was p, and the probability of failure was q, which is forced to be 1 minus p, because there's only 2 outcomes, right, is this. This is the probability of exactly k successes. So, because they're independent, you can multiply. It's, all right, probability of success, k times, and then probability of failure the rest of the times. And then we have to talk about all the different ways that you could have achieved k successes out of those n trials, because, like, maybe the first k trials were all successes and the rest were failures. Maybe they were interspersed in between. We have to think about all the different ways that we could have gotten success. Which trials were the ones that were successful? So that involves combinations, okay? So let's talk about this and hopefully prove to you why this makes sense, this probability, okay? So here's an example. The probability of flipping exactly 2 heads after tossing 4 coins, okay? Let's figure this out. This, following the formula, it's going to be, all right, probability of flipping exactly 2 heads after tossing 4 coins. Well, it's going to be the probability of success, which is 0.5, right? Because it's a fair coin. There's a 50-50 chance that you got heads. And so it's exactly 2 heads and exactly 2 tails. So what's the probability of failure? That's 1 minus 0.5 for the rest of the time. So 4 minus 2 is, again, you got 2 failures. And now we have to think of all the ways that we got those 2 successes and 2 failures. So it's 4, choose which ones were the successes, for example. Because here's what could have happened. You could have gotten, let's say that heads is a success. You had 4 outcomes, right? They could have been heads, heads, tails, tails. They could have been, the heads could have been right here, and the tails could be here. The heads could have been at the end. The tails could have been here. And then finally, it could have been heads, tails, tails, heads. Those are the 4 ways, I think. There actually might be more. Let me think about this. What does 4 choose 2? It's 4 times 3 over 2. So there's actually 6 of these. So there's 2 more places for me to put 2 heads that I have not yet noticed. Oh, it could have been this one, heads, tails, and then we have the opposite as well. So it's tails, heads, tails, heads. So these are all the different ways that you could have had 2 successes. Do you see that? That's where the 4 choose 2 comes into play. That's the different number of ways that you could have that, okay? And then that gives us the final probability if we multiply this by 0.5, and really this, you can bring them together now, it's 0.5 to the 4. Okay? So that is apparently, I did this ahead of time, it's 0.375. So there's like a 38-ish% chance that you flipped exactly 2 heads when you tossed 4 coins. Okay? Which is smaller than you would expect. Yeah? Maybe because it has to add up to 1, right? That's why it's a bit smaller than you might expect. So 38-ish% chance of you flipping exactly 2 heads after tossing 4 coins. And that's how you use this binomial distribution. Hopefully that makes sense. So we can also use this to talk about the expected number of successes, because that involves expected values, right? What's the expected number of successes for each trial? Let's call each trial x sub I. Well, here's the answer for each trial, right? It's going to be the probability of success times a 1. So that's because we're counting it. If it was successful, that's going to give back a 1 for our random variable, and 0 if it was false, 0 if it was a failure. So it's p times 1 plus q times 0, or 1 minus p. Those are equivalent because there's only 2 outcomes. And so this random variable is a 1 whenever it's successful, and it has a probability of success p. Well, the answer for this expected number of successes then is p itself. Okay? And this is very easy to now think about things. So if you have n trials total, the expected number of successes is n times p. If they're all the same, that is. So that's because of that linearity of expectation. So for example, let's make a random variable for me flipping a coin. This is the ith coin that I flip. The expected value of successes, the expected number of successes for a single coin flip is just the probability of me getting success. So let's say that success is heads, and so it's 0.5. That's the expected number of heads that I see on each coin flip, okay? And using this, using our expression here, the expected number of successes over a few trials, if I flip 3 coins, that means that I should expect to see 1.5 successes, 1.5 heads. Does that make sense? Using this linearity of expectation, because I'm doing this. I'm doing the expected number of a constant number of things times my random variable x. That's just, well, c, 3 in our case, times the expected value of x, which is just c times our p, our probability of success. So it's very easy to calculate the expected number of successes using this formula for Bernoulli trials. Okay? And so the distribution of all of these things, of all these successes over different numbers of trials, it is called the binomial distribution. Okay? It looks pretty if you graph it, but this is all that I wanted you to see here. All right, so now let me have you use this formula yourself, and that'll do it. All right, so let's pretend that we're gambling. So we have a coin, and we're not sure if the coin is fair. Okay, so we flip a coin and we try to see if it's fair. So it's either fair or is biased. All right. So if a coin is fair, that means it's equal probability heads and tails. If it's biased, if it's a fake coin, it's a bad one, then we think that the probability of heads is equal to 0.3. That's, I guess, that's the only kind of fake coin you can buy. So we know it's either fair with equal probability or biased with the probability of heads being 30%. Okay? And we're not sure which coin it is, which coin the gambler has, which coin we have maybe. So without knowing that, we ask the person to flip the coin 10 times. And we want to see, was it fair, was it biased, based on those 10 flips, all right? If the number is heads, if the number of heads is at least 4, we conclude that the coin is fair. And then our idea is, was that a good number of a cutoff? Okay, if the number of heads is less than 4, we conclude that the coin was biased, because it's supposed to land on tails a lot more if it was biased. All right, so if the number of heads is at least 4, we conclude that the coin must have been fair. If it's less than 4, then we think it's biased. So let's calculate the probability that we were wrong. Okay, what's the probability that you reach an incorrect conclusion if the coin is fair? So think about that. And then what's the probability that you reach an incorrect conclusion if the coin is biased? Think about that as well. Okay, so pause the video, give this a try, and then let me draw some pretty pictures and see if it works. Okay, so if we had a fair coin, it's my best drawing of a coin. If we had a fair coin, then the probability of you getting heads was 0.5. If we had a biased coin, the gambler had a biased coin, then the probability of you getting heads was 0.3. That's success, apparently. And so for part A, what's the probability that you reach an incorrect conclusion if the coin is fair? That means we ended up seeing less than 4 heads, but it was really a fair coin. Okay? So less than or equal to 3 heads is what we saw. Okay? And so we need to figure out the probability of that happening with a fair coin. Okay? And we can use our binomial distribution for that. Okay? The probability of exactly that many successes. So this is what we need to calculate. What's the probability with a fair coin that we saw 0 heads, the probability that we saw 1 head, the probability that we saw 2 heads, and the probability that we saw 3 heads. And then, if we add them together, that is the probability of us seeing exactly those things happening. Okay? What's the probability that we saw 0 heads, or 1 head, or 2 head, or 3 heads with a fair coin? Okay? So let's do this. Well, it's always 10 coins being flipped, right? It's the gambler is flipping 10 of those of that fair/biased coin, and so this probability using our formula is 10 choose 0. That's the number of successes. Heads is success. And if it was fair, it's 0.5, right? For each 0.5 times 0 for 0 heads, and then we had 10 tails, right? And then the probability of seeing one head is going to be 10, choose one success. So it's 0.5 if it was fair, we saw one head, and then 0.5 for 9 of those tails. Okay, there are 9 other tails that showed up. And then we can keep on calculating this for up to 3. And that will give us the probability that we saw 3 or 2 or 1 or 0 heads, given that it was a fair coin. Those 0.5s in each for success and for failure, for heads and for tails. And so apparently, if you do this all together, the answer is 0.172. Is that what you found? So it's pretty unlikely that you were wrong if the coin was fair, which is nice. Let's try this one. So what is the probability that you reach an incorrect conclusion if the coin is biased? So that means that the coin was biased, but we thought it was fair. Okay? So we saw at least four heads. Oops. We saw at least 4 heads, and the coin was actually biased, but we thought it was fair because we saw so many heads. So that's the probability of 4 heads with the biased coin using that formula, plus the probability of you seeing 5 heads with the biased coin, all the way to the probability of you seeing 10 heads with the biased coin. Because there's 10 total, right? And so this, if you break it down again, it's all right. 10 choose 4 times the probability of you seeing heads 4 times. That's 0.3 with the biased coin, right? To the 4th power. And then there's 6 other tails, which had 0.7% chance with the biased coin of occurring. Boop. And so if you add all these together, it looks like the probability is going to be, if you do all this calculation, it's 0.35. Okay, so a 35-ish% chance that you were wrong when the coin was biased. Okay, so the odds seem to be in your favor, but this is all a game of chance. It's all probability based, right? So there's a possibility still. There are universes where you were wrong, even though you asked the gambler to flip that coin 10 times. I think you can imagine that if you asked the gambler to flip the coin 100 times, you'd end up with better odds of being correct, but still not perfect odds. That's the beauty of probability. Okay? So finally, I just want to bring this all together and talk about computer science stuff for one last slide. Let's talk about hashing, okay? This has to do a lot with probability. So in hashing, when we make a hash table, we like to make sure that our hash function is nice, and we want to make sure to split up our values among all the possible bins that we could put them in, right? A hash table is just a finite array of places that you could put your key value pairs, right? You only have so many places. And there are different ways to handle collisions, like you could use lists, for example, ... if you have collisions, but we would like to minimize collisions. We'd like to make sure that each bin is equally likely for every value of your key. Okay? So we'd like to calculate what is the probability of a collision in a hash table when you have n slots for your hash table. That's the number of bins you could put things in, and then m keys possible to insert. Like we know the user is going to insert 100 phone numbers, for example, but we only have 25 bins to put and use our hash table with. All right, so we can calculate this kind of probability, and it's useful to want to do, and very fun, very computer sciencey. So this probability is 1 minus the probability that there are no collisions at all. Does that make sense? That's the easier thing to calculate. So that's equal to 1 minus, what's the probability that there are no collisions? That's like, all right, the first key had no collisions times the probability that the second key had no collisions times the probability that the third key had no collisions, because these are all independent things, right? You can multiply those times the probability that your last key that you inserted had no collisions. So in the best case, all of those keys that you're trying to insert are random, and each slot is equally likely. So this is our probability. So the first key has no collisions. There's a 100% chance there are no collisions because there's nothing else in the table. And then the next one is, all right, n minus 1 over n, right? Because now you've used up one slot. You have a pretty high chance of not colliding with that one slot that you filled, but there's still a chance, right? And so the probability that the third key has no collisions is n minus 2 over n, and you keep on going in this order, okay? So, for example, if n was 2 to the 32, like we had a giant hash table, it could hold 2 to the 32 things. So every int was a possibility. We have every int being a slot in the hash table. And then we were trying to insert 77,000-ish things. Here are the odds of you getting a collision. So for example, this is how many hash values you have in a 32-bit hash table. That's, you had 2 to the 32 slots, but you're inserting just this many things. Your odds of a collision are still 1 in 2. It's not 0. It's a 50-50 chance that you've ended up with a collision. Even though there are billions of slots, you only inserted like 77,000. You still have a good chance of a collision. 50-50 chance. Okay? You'd prefer smaller odds, right? So maybe you have a giant hash table, but you're only inserting 294 things. Then your odds get better. Okay? That's the idea. So if we can, we want giant hash tables if we have that much memory, because our collision odds are very, very small. Smaller than the odds of a meteor landing on our house, apparently, which is a fun thing that somebody's calculated. So yeah, this brings it all together. This is computer science. This is why we care about all this stuff. We want to be able to know how good our implementations are, and sometimes we have to bring probability into the mix. And this is a great example of that, I think. So this is probability in a nutshell. Now we are all experts. Go off and do your homework assignment about it, and have fun. So I will see you in the next lecture.